Welcome to this number theory primer. Today we'll be discussing a very important theorem called Euclid's theorem, and let us recall some relevant things. So suppose we have two integers a and b, then we define a non-zero integer as a common divisor if it divides both of them, and if a and b are not both 0, then we define their greatest common divisor as the greatest of all common divisors, meaning you collect all the common divisors and take the maximum amongst them. There exists a maximum, we argued that. It's a very simple argument. And lastly, we also saw, which in this lecture we are not going to use, but still, suppose you write a as bq plus r, then gcd a comma b is gcd b comma r. Okay, so here are two simple problems. The first one I marked as star because I'm going to use it. It's a very, very straightforward problem. All right. So here is Euclid's theorem. Suppose you fix two integers, not both 0, meaning one of them can be 0, but not both of them. Then we want to show that there exist integers x and y such that gcd a comma b is ax plus by. In other words, the greatest common divisor of two integers can be expressed as an integer linear combination. Such a thing is called an integer linear combination of a and b. So that's the theorem, and let's prove it. So let S equals the collection of all the integer linear combinations that one can form using a and b. But we will throw away all the non-positive ones. So collect all the integer linear combinations that you can form using a and b, but only retain those which are positive. So that's our set S. And let's see that S is non-empty. So S is non-empty because one can argue that in several ways, but one way to argue is just note that a times a plus b times b is an integer linear combination of a and b, of course, and it is also positive. So this a square plus b square has to be a positive thing because not both of a and b are 0. And clearly it is an integer linear combination of a and b. Just substitute x equals a and y equals b. So therefore S is non-empty. And if you have a non-empty set, then by well-ordering principle or common sense, it has the smallest element. If you have a non-empty subset of integers, if you have a non-empty subset of natural numbers, then it has the smallest element. That is well-ordering principle or common sense. So let D be the smallest element of S. Right? And we will show, so this will be our final goal. We will show that D is the GCD of A and B. So once we show this, we will be done, because then D in particular lies here, and hence it would be expressible as an integer linear combination of A and B. So once we show this, we will be done. So also note that in the course of the proof, it is revealed that the greatest common divisor is the smallest positive integer linear combination that you can form using A and B. That will be clear when, that will be that is exactly what we are trying to show actually in this yellow line. All right. So since D is an element of S, we have that D is an integer linear combination of A and B. So let these be integers such that D equals ax naught plus by naught. And we claim that D divides A. So once again, our goal was to show that D is the GCD of A and B. Once we do that, we'll be done, because clearly D can be expressed as an integer linear combination, and if D is GCD, then GCD can be expressed as an integer linear combination of A and B. All right, so in particular, we should be able to show that D divides both A and B. If this is our goal, this is a more modest goal. So let's achieve that. And here is the proof. So once you want to show something divides something, you resort to the division with remainder theorem. So write A is equal to dq plus r for some integer q, and some integer r in this range. So that's immediately by the division with remainder theorem. We want to show that r is 0, because once we do that, a would be divisible by d. So now we just use this expression for d. So a is equal to ax naught plus by naught q plus r, which implies a into 1 minus qx naught plus b into minus qy naught. Is that correct? Yeah, that is fine. So this is equal to r. All I did was shuffle things around. Just put r on the right side and take everything on the left side and you'll get that. So we see that r can be written as an integer linear combination of a and b. That's what this says. But if r were positive, if r were non-zero, then it would necessarily be positive. So if r is non-zero, then it is positive, and at the same time, as we have seen, it can be written as an integer linear combination. So it is both here, and hence it would be in S. But r cannot be in S because it is smaller than d, and d is already the smallest element in S. So since r is smaller than d, we have r does not belong to S, and hence r is not positive. So this is symbol for not positive, because if r were positive, it would become an element of S. It is already expressed as an integer linear combination of a and b, and if it were positive, then it would be in S. So the only possibility for r is that r is 0. And this proves the claim, because once r is 0, clearly a is a multiple of d. So that proves d divides a, and similarly, by the exact same reasoning, one can show d divides b. Right? So from the above claim, we have d is a common divisor. That's exactly what the above claim is. Thus t is a common divisor of a and b. And therefore it cannot be greater than the GCD. A common divisor is always at most the greatest common divisor. So therefore D is at most the GCD of A and B. However, since D is of this form ax naught plus by naught, GCD divides A, GCD divides B, and therefore GCD divides this. This was the first problem. And therefore GCD divides D. So, but of course, GCD of A and B is in particular a common divisor of A and B. So GCD divides A and B, and hence GCD of A and B divides ax naught plus by naught by first problem, which implies GCD divides D, which implies GCD of A comma B is at most D. Since D is a positive integer, you have a divisor of it. So divisor is going to be at most that positive integer. So if we just look at this one, let's call it star, and that one, let's call it double star. Then by star and double star, we have the GCD A comma B equals D, and we have achieved our goal. This was our goal. We have expressed D as an integer linear combination of A and B, and that's exactly what Euclid's theorem says. All right, so we have proven Euclid's theorem. In the next lecture, we'll give a different proof, a slightly different proof, just like we gave a different proof of the division with remainder theorem. And now let us look at a consequence of Euclid's theorem, immediate consequence. So suppose we have again two integers, not both of them are 0, and D is a common divisor of A and B. Then it divides the GCD. A common divisor of A and B, we know, is at most the GCD, but this says even more. It says that it's strongly less than GCD in some sense. So why is that? That's because we can find there exist integers such that GCD A comma B equals ax plus by. And y. So this is because of Euclid's theorem. And because d divides a and d divides b, d divides this guy, and hence d divides GCD. So dot dot dot, just fill in the details. And that's it. So every common divisor divides the GCD. All right. So with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.